presentation of our invitees. I am today honored and proud to introduce Professor Hanley and Anastasios Panagiotelis for our March webinar. It's not the first time you are listening to them. Mrs. Hanley is an associate professor at the Center for Actuarial Studies of the University of Melbourne inside the Department of Economics, while Sir Anastasios Panagiotelis is an associate professor in business analytics at the University of Sydney. Therefore, we are very proud to greet our Australian colleagues. Professor Hanley is leading the research project Who, When and Where Assessing Mortality Risk of Climate Change, which was funded by the SCOR Foundation from 2023 to 2024, and we are therefore at the end of this project, while Professor Anastasios Panagiotelis is co-investigator on the project. The today's webinar aims to present the final conclusion of the project, whose ambition was to provide insight into how climate change is likely to affect mortality experience across age, seasons, and geographical locations. The webinar will focus on the presentation of a Bayesian modeling approach that quantifies the impact of temperature on mortality in over more than 300 climate divisions in the US. The researchers will show key findings based on the model estimates, demonstrating spatial dependence and variations in temperature-related mortality risk. Scenario-based analysis are then conducted to estimate excess deaths due to temperature projection, therefore virtually in the future, under different climate scenarios, providing further insights on regions that are most vulnerable to climate change. Professor Hanley and Anastasios Panagiotelis, thank you so much to have accepted to present your conclusions to a wider audience. Of course, auditors can read the scientific report they will find on the website of the foundation with a lot of mathematics, etc., and statistics. Professor Hanley and Anastasios Panagiotelis, you have now the floor for, let us say, a maximum of 1 hour. You can go slightly beyond, but roughly speaking, after which we will have a Q&A session for a maximum of a half hour. In any case, we will close the webinar at 3:30 Paris time, that is 1:30 hour. For the sake of efficiency, I will ask auditors to please postpone their questions to the Q&A session and to limit their questions during the presentation to only those relating to material difficulties in understanding on or hearing. Please, Professor Hanley, Professor Anastasios Panagiotelis, you have the floor, and thank you so much.
Thank you so much, Philip. So let me share the slides. Can everyone see my slides? Tas, is that okay? Can you see the slides?
Of course,
okay?
It's okay. If you can put it on full screen, it will be better.
Okay. Is it working now?
Yep, perfect.
Yeah, okay. All right. Thanks again, Philip. Hello, everyone. My name is Han Li, and I'm from the University of Melbourne. It's my pleasure today to share with you all our latest research on temperature-related mortality risk. And I'll be presenting together with my research collaborator, Associate Professor Anastasios Panagiotelis from the University of Sydney. So today I'm going to talk about projecting future mortality rates under different RCP scenarios. And this is our second presentation based on the project sponsored by the SCOR Foundation for Science. And the project title is Who, When, and Where? Assessing Mortality Risk of Climate Change. So we would like to express our sincere gratitude to Philip, to Zeying, and to Adam for their generous support and help throughout the project. And here is the outline of the talk. First, I'm going to talk about the background and the motivation, and then data description and visualization, and then explain what RCP scenarios are about. Then I'm going to hand over to Anastasios for modeling framework and the results based on from scenario-based projections. Okay, so let's start with the background and motivation. In this project, we focus on temperature-related mortality risk. So the first question to answer is how temperatures affect mortality. Globally, approximately 5 million deaths were associated with non-optimal temperatures per year, and that is 1 out of every 10 deaths in the world during 2000 and 2019. So we know temperature is a key factor in mortality risk. First of all, we know there is seasonal fluctuations or seasonality in mortality experience, which means that mortality is generally low in summer and high in winter. And this is particularly true for older generations or older age groups. And beyond the normal range of temperatures, we also know about the adverse impact of extreme heat or extreme cold on mortality and population health. For example, for extreme heat, such as heat waves, we experience an excess level of mortality from certain causes, such as heat stroke and cardiovascular strain and kidney failure. And on the other hand, for extreme cold temperatures, for example, for a cold spell, we will experience excess mortality from respiratory infections, and again, cardiovascular strain and hypothermia. And we also know that these extreme temperatures disproportionately affect older adults. And for different regions and different socioeconomic group, they react to extreme temperatures differently. And finally, I want to note that climate change is indeed increasing the frequency and intensity of extreme heat waves. On the other hand, cold-related deaths may decrease in some regions. So imagine global warming increase the temperature in winter. And for certain regions, that may result in a decrease in mortality because the winters are becoming milder. So on the next slide, I summarize the research objectives for our projects. Basically, we're looking into 3 questions. Who are the excess deaths? When do excess deaths occur? And where are the excess deaths? So when we talk about excess deaths in this project, we're talking about excess deaths in the context of temperature-related mortality risk. So the proposed modeling framework is built upon these 3 objectives, and more importantly, how can we use the proposed modeling framework? A very important point is we're going to use the proposed modeling framework to assess future level of climate-driven or temperature-driven excess mortality. And in short, basically what we're doing is projecting mortality risk under different RCP scenarios. So RCP scenarios, basically different climate scenarios, which I'm going to explain a little bit later. So for the empirical study of this project, we collect data. We collect both temperature data and mortality data or death data for the United States. So throughout this presentation, our illustrations will be based on the US data. And we first collect monthly temperature data, which includes both minimum temperature and maximum temperature at the climate division level from the NOAA for the contiguous United States. So on this map, you can see that so these climate divisions, they are in total 344 climate divisions. They are much smaller than states, but larger than counties. And this map is basically from NOAA, and it shows the average temperature at climate divisions for February 2025. And you can already see the variations in average temperature across the US. And for the mortality data, we collect US county level monthly death data for the period 1968 to 2018 from NCHS and CDC Wonder database. So here I plot a map which illustrates the counties in the US. And there are more than 3,000 counties in the US. And you can see the size of the granularity is much finer. However, in this project, because we're going to use climate divisions as shown on the previous map as our geographical unit, obviously, before we do any modeling exercise, we need to convert the county level deaths into climate division level deaths. And this requires some pre-processing of the data. And basically, we're going to aggregate the county level death data into climate divisions. And on the next slide, I have a snapshot of the log mortality at climate division level for the US. And the data is plotting for log mortality for ages 75 to 84, and the data is based on January 2018. And from this plot, you can see the inequality in mortality experience or life expectancy. Already you can see the differences in the southern states. In a lot of the southern states or the climate divisions in the south, the mortality rates are generally higher, especially comparing to the East Coast and the West Coast of the US. So we do need to take this natural variation into account when we conduct the modeling exercise. We need to keep in mind that these different geographical areas, they would have some different characteristics when it comes to mortality experience, because temperature or climate is not the only factor that affects mortality experience. And as I've mentioned before, the focus of this presentation is to understand temperature-related mortality risk under different climate scenarios. So in the next section, I'm going to briefly explain RCP scenarios and their implications on temperatures. So the question would be, what are the representative concentration pathways or RCPs? So RCPs are climate change scenarios to project future greenhouse gas concentrations. These pathways or trajectories describe future greenhouse gas concentrations and have been formally adopted by the IPCC. And initially, IPCC developed 4 different RCPs namely RCP 2.6, RCP 4.5, RCP 6, and finally RCP 8.5. So these scenarios are labeled after the expected changes in radiative forcing values for the year 1750 to the year 2100. So on the right-hand side, I have a plot visualizing the differences in carbon dioxide emission across these 4 different scenarios. But by simple words, RCP 2.6 is a very stringent pathway, which requires that the carbon dioxide emissions start declining by 2020, which has already passed, and go to 0 by 2100. So this is the most stringent pathway, which is less feasible given the current trajectory. And then the second one, RCP 4.5, is an intermediate scenario in which emissions peak around 2040 and then decline. And this is considered as the most probable baseline scenario. And RCP 6 is also an intermediate scenario, which is it's often referred to as a stabilization scenario, where emissions peak around 2080 and then decline. And finally, the RCP 8.5 is often considered as the basis for worst-case climate change scenarios, where emissions continue to rise throughout the 21st century. So these are some basic background information about representative concentration pathways. And now let's look at the impact of these different pathways on global temperatures. So on this slide, I have a snapshot on annual minimum temperatures, and this is under the RCP 4.5 scenario. So you can see from the color bar, blue represents cold temperatures, and the color red represents hot temperatures. And this is based on the lower emission scenario. If we switch from RCP 4.5 to 8.5, then we can see that there will be an increase in the temperature. So again, I'm doing this again. You can see the difference. The red part, or the reddish part of the plot, is bigger, and the upper part becomes lighter in blue. So if you compare this side by side, you can see the difference. And by the way, this projection is for the period 2090s. Okay, so for the 10-year period from 2090 to 2100. And similarly, we can look at the annual average maximum temperatures under the 2 RCP scenarios. So on this slide, I'm plotting the maximum temperature under RCP 4.5. And then when we switch to RCP 8.5, the plot becomes redder. So I'm going to do it again, and you can see the difference switching from 4.5 to 8.5. There will be the maximum temperature is going to be higher across all regions, but a certain region will have a bigger impact comparing to the rest. And again, this is a projection for the period 2090 to 2100. So this is for illustration purposes, and the data and plots are generated by from the NOAA website. So now let's look at the annual minimum and maximum temperatures for a specific region. So because these are the snapshots for the entire US. Now, we want to look at the minimum and maximum temperatures for a specific region. And I pick Orange County in California as an example. So on this slide, there are two plots. The one at the top illustrates the minimum temperatures, and the one at the bottom is showing the maximum temperatures. And we also have two different colors. The blue color represents lower emission scenario, and the red color represents the higher emission scenarios. And when we look at these two solid lines, the red line and the blue solid line, these are the mean projection on minimum or maximum temperatures for Orange County in California. And this shaded area in red or shaded area in blue gives you the upper bound and the lower bound for these projections. And from these two plots, we can see that comparing the different scenarios, so lower emissions basically is equivalent, in our case, equivalent to RCP 4.5, and we call higher emission scenario basically RCP 8.5. We can see that there is a divergence in the average temperature for both minimum and maximum over time from 2000 to 2100. You will see under these two scenarios, eventually there will be a divergence in the minimum and maximum temperatures. So global warming is happening. Especially like you can see the difference between different across different climate scenarios. So what I have just shown you would be for the annual minimum, annual maximum temperatures. So we then look at the monthly projections again for the same geographical area, and this time I'm going to illustrate two time periods. So this would be the monthly minimum temperatures on this slide, and the first projection is for 2035 and 2065 average. So this first plot illustrates the projected minimum temperatures for Orange County, California during 2035 and 2065. And then the bottom plot represents the monthly minimum temperatures of the projected monthly minimum temperatures for the average 2060 to 2090. And obviously, for the 2060 to 2090 average, it's going to be higher in general comparing to the 2035 and the 2065 average. And the other thing is you can see the divergence again. So the two solid lines, the red solid line and the blue solid line, for the first plot, they are relatively closer comparing to the two solid lines in the bottom plot, which shows the 2060 and the 2090 average. So basically, this is telling us the same story. And if we switch to the monthly maximum temperatures, we have almost exactly the same observations. So the reason why I'm showing you these two slides on the monthly minimum and the monthly maximum temperatures is because this would be the inputs that we're going to use when doing scenario-based projections. So we're going to use not only the Orange County, we're going to use the information across contiguous US, but basically these monthly maximum and minimum temperatures for the two time periods that we are considering would be the input to generate scenario-based projections to assess mortality risk between different climate scenarios, namely between scenario RCP 8.5 and RCP 4.5. So obviously this is very very relevant to the modeling framework that we have developed. And now I'm going to hand over to Anastasios, and who will be talking about the modeling framework and the projection results. So, Thus, you can be sharing the screen.
Okay, so am I sharing the screen now? I think.
Can you put it in full screen? Okay, it's fine.
Okay, so you can see now? Yep.
Yep.
Okay. Okay, so thank you for the handover, Han. And before I get into the weeds of the modeling framework, I would like just to thank Philippe and Ziying for providing us the opportunity to present this research. I recognize many of you from an earlier presentation of the intermediate results, and I'd like to thank those people that were there in that intermediate presentation, since they provided good feedback, which we've incorporated into the modeling framework. Nonetheless, I will just quickly rehash the modeling framework. So some of this will be familiar to those of you who were at the intermediate talk, but for the benefit of those that were not, I'll just briefly go over the salient features of the model, as well as describing what we've changed so that we can really look at the projections under different RCP scenarios, and in particular, the interplay between that and different climate divisions. So just briefly, the proposed model is given by YIXT. So 3 indices. I is an index for climate division, so the geographical region, T for time, and X for an age group, and YIXT is the annualized log mortality. So we're looking at log mortality rates, and that's equal to a mean plus some Gaussian noise. And the mean is made up of various random effects as well as regression effects. So temperature comes into the model via its mean. And I'll get to that in a few slides. Before getting to that, just some important features of the model. So the data that we used here does have a large degree of data suppression. So for more sparsely populated climate divisions, there can be so few deaths that they do not report the exact number of deaths. And that happens at the number of 10 deaths. If there's fewer than 10 deaths, then we don't have the exact number of deaths. So what we compute where it's available is the deaths divided by the population. And then we just multiply that by the days in year divided by the days in month to annualize that figure and take the log. But if there's fewer than 10 deaths, we don't observe YIXT, but we do know that it's upper bounded by a value given here. So basically the deaths is upper bounded by 10, and this expression will be upper bounded by the same thing, but with 10 replacing the number of deaths. What that means is that there's a slight adjustment to the model. YIXT now becomes YIXT star, and that's a latent variable. So that if the data are not suppressed, YIXT star is equal to YIXT. If the data are suppressed, then YIXT star follows a truncated distribution, and it's truncated from above at that value of U that was on the previous slide. The reason I raise this is that already this problem necessitates a Bayesian approach, since models with these sorts of latent variables are very amenable to Bayesian estimation. But the real core of the model, the real heart of the model, is in the equation that you see here. So this is now the mean of log mortality, and that's given by an intercept. There are then some one-way random effects, so gamma ICD for climate division, gamma year, so a time trend across the different years, as well as gamma X age, so an effect for the different age groups. So those are the effects given in orange. We can think of these as controls. Something else that we found quite important to model is an interaction between the time trend and age groups. I'll present some results later on that show some interesting characteristics of that part of the model. But the focus for today's talk is really going to be on these last two bits here, because this is how temperature enters the model. And when it comes to looking at projections of log mortality under different climate scenarios, this is the part of the model that matters. So what do we have here? Well, this is, you may recall from the first presentation, this was simply a function of temperature. Now we actually, and one of the bits of feedback we got was that, well, you should look at maximum and minimum temperature. And effectively, that's what we've done with a slight tweak. What we're looking at here is actually the range, so the difference between maximum and minimum temperature, as well as the midpoint, the arithmetic mean of those two values. And each of those enters into the model with through a different function. So Fi and Gi are non-linear regression functions. So these temperature variables can have a non-linear effect. And crucially, they vary by I. They vary by the climate division. So temperature can have a different effect for different climate divisions. And this is quite important for quantifying or determining which climate divisions have the most resilience to potential climate change. And I'll have some things to say about that once I get to the main results. So just as a bit of a teaser for what those main results look like, essentially what we're going to do is feed in temperature ranges and temperature midpoints for the RCP 85 scenario. We're going to do the same thing for the RCP 45 scenario. If we take the difference of those two things, all the other effects cancel out, and then that gives us a sense of the relativity between the two different emissions scenarios. And that allows us to kind of quantify what will be the effect of the RCP 85 scenario relative to the RCP 4.5 scenario. So that's the model, and in particular, the relevant part for how we use it is the bit here in red. Now, just a quick slide on why we looked at range and midpoint. So as I mentioned earlier, the suggestion from our intermediate presentation from this audience was to look at monthly maximum and monthly minimum. And this makes perfect sense. For example, a high minimum may be a better indicator of a more severe heat wave than a high maximum. So we've all experienced that. I think this is a mostly European audience, so I'll speak in degrees Celsius. But, you know, people can withstand a day in the high 30s, but it's when the nights are continuously also in the high 30s that the heat wave feels more severe, and in fact that can lead to higher mortality. So minimum and maximum temperatures are both important when we look at this. The problem we had with just using minimum and maximum temperature as they were is that they are very highly correlated. And that led to some instability in the estimation that we were looking at. So again, even if you're not a statistician, but you've done some regression, you would know that dependent variables that are highly correlated can lead to difficulties in estimation. Now, when we take the range and the midpoint, this correlation is, well, I say here removed, there's still a little bit of residual correlation left over, but the correlation is greatly reduced when we look at the transformation of the range and the midpoint. And essentially, we're using the same information. Okay, the maximum and the minimum can be retrieved from the range and the midpoint. But by modeling the range and the midpoint, we get more stable estimation because there's less correlation. It doesn't impact anything about how we do the projections. All we have to do is take our RCP scenarios and similarly transform those before we feed them into the model. So this is just a technical issue mainly to allow for more stable estimation. I'll briefly talk about how we actually get nonlinear relationships here. So these nonlinear functions are modeled as what are called linear combinations of B-splines. So the capital B here is a function that can be pre-computed. And then the beta j's are just coefficients. So what we effectively do here is take a nonlinear model, but write it down as a function as a linear function of parameters beta j. And then those beta j's are the parameters we estimate. So although it's a nonlinear model, it reduces down to something that can be estimated in a linear fashion. This is a very flexible structure. It can capture a wide range of nonlinear relationships. Here's just a few demonstrations. So what you see in blue are what we call this B-spline basis, these B functions, and the orange lines are just different types of functions that can be estimated as linear combinations of those blue functions. So you can get on the left-hand side something that's quite close to linear. On the right-hand side, you get a parabola, and in the middle, you get something that's very wiggly. All of these functions can be estimated as linear combinations of B-splines. So this is what we use to estimate our temperature effects. And again, just a few last things about the model. Again, it's a Bayesian model, so there's something in there about priors. The model is very highly parameterized. So for the full US, there would be close to 7,000 parameters. But there is a high degree of structure in those parameters. For instance, when it comes to ages, we know that the random effects for age for people in, say, the 45 to 55-year-old age group should be similar to those for the 55 to 65-year-old age group. Similarly, for the climate division, some of these climate divisions neighbor one another's. Therefore, the basis coefficients for those climate divisions that are neighboring one another should be somewhat closer to one another. So what we do is we incorporate what are called ICAR priors, which have a history going back to the 90s. And the basic idea is that we shrink estimates of neighboring parameters closer together. What do I mean by neighboring parameters? Well, it might be the random effects or the B-spline coefficients for climate divisions that share a border. Or it might be random effects for consecutive years, random effects for adjacent age groups, or coefficients of B-splines that are next to one another. I spoke about this at length in the intermediate presentation. I'll go over it a bit quicker here today. But the basic idea is that we're exploiting the structure in the model. And that's what allows us, with quite limited data, to estimate a very highly parameterized model. Some last few points on the inference there. So the inference is fully Bayesian. The details of what we use is it's a Hamiltonian Monte Carlo algorithm. It's called NUTS, the no U-turn sampler. It's implemented in a software package called STAN. And what we actually obtain is a full sample from the posterior distribution. So for all of the parameters, we can actually get complete uncertainty quantification. We can get confidence intervals and prediction intervals. I won't show too many prediction intervals on the results today, simply because I want to visualize a few things at once, and it kind of impedes the visualization. But all of those confidence intervals and prediction intervals are available. Since it's quite a large model, what we found is that it helped if we actually estimated the model separately for 6 subregions of North America. And again, this also facilitates the presentation of results. We are thinking about estimating the full model using an approximate form of inference, but that's not what I'll be talking about today. Okay, so before getting to the results on the different RCP scenarios, I just want to briefly go over the estimates of the model. So before we do projections, as a sanity check, let's make sure the estimates of this model make sense. And I'll focus on 2 of those subregions. The first, and it's the one that you see on the left-hand side, is known as the Southern Plain. And it's actually, so the Plains region is this region in the center of the United States. And this is quite an extensive geographical region. It starts right up here in the north. So this bit you see at the top is the border with Canada. And it goes all the way down to the very bottom, to the very south. Right down there, that tip at the bottom is the southern tip of Texas. So a very large range of climate divisions there. What we see here is that climate divisions that are in a darker shade of blue have higher mortality rates relative to those that are in lighter shades of yellow. And what we can see here is there is a geographical pattern, and that is in some ways associated with the socioeconomic condition of some of these regions. For instance, Oklahoma, which is sort of here in the middle, is a poorer state and has higher random effects and higher mortality. What we see over on the right-hand side is a similar thing for what is called the Central East Atlantic part of North America, but is probably better known, especially to a US audience, as really the Northeast. So New York City is here, Boston is somewhere over here. And again, what we can see here is different mortality experience of these areas. Some of these coastal areas closer to New York City have quite a low random effect, which is associated with lower mortality rates. But if we look at West Virginia, and West Virginia is a very poor state, we can see darker shades of blue, meaning higher mortality rates in West Virginia. So there's no projections yet. That's just the estimates of the model. But what it allows you to see is the richness of output that we can obtain from this model. And it does indicate to us where mortality experience is at its best and where it's at its worst. Although it's not the main focus of today's talk, I thought I'd just show the time and age effects in those two regions. There are some interesting results coming out of there. So essentially what we're looking at here is in each panel, we're looking at a different age group. On the 4 panels on the left, we're looking at the Southern Plain region. In the 4 panels on the right, we're looking at the Central East Atlantic region. And one of the interesting features here is that for the mostly here what we're seeing is that mortality rates go down over time, and that accords with what we would expect. Advances in medical technology are there. People smoke less. There's all sorts of reasons why mortality goes down over time. But an interesting aspect of this is the 55 to 64-year age group, because what we're actually seeing there is that post 2010 up to about 2020, we actually saw mortality rates go back up for that particular age group. And that's a fairly well-documented phenomena, both for that 55 to 64-year-old age group and a slightly younger age group. And a lot of this is to do with, again, elements of socioeconomic disadvantage. This is particularly pronounced in the deindustrialized regions of the US, the so-called Rust Belt. It's associated with the deaths of despair, addiction to opioids, and these kind of problems. So that's a well-documented effect, and our model is able to pick that up. Finally, I'll just present, and again, these are not for every climate division because there's over 300 of them, but this is a few climate divisions in the Southern Plain. What you see on the left is the effect of average temperature on log mortality. What you see on the right is the effect of range. And again, this accords with what we would expect to see. The range of temperature, so the maximum minus the minimum, when that is low, that is often telling us that it is staying cold when it's cold. Both the maximum and the minimum are close to one another, but low. Or alternatively, that they're both high, but close to one another. So low ranges are associated with higher mortality. And again, that makes sense. That is the persistent heat wave or the persistent cold snap. And that's really the main driver out of the two measures that we look at here. That range is a big driver. So that answers the question that came up in the previous talk. And then what we see here is if we look at the average temperature, generally higher temperatures are associated with higher mortality. Keep in mind that is the case after we also include range in the model. So if we were to just look at average temperature on its own, we would get that very commonly observed U-shape effect. We don't get that here because we're also looking at range. And although we did remove most of the correlation, it is still the case that lower ranges are associated a little bit more with colder temperatures. So some of that effect of the cold temperatures is actually picked up here by the range instead. But something else I want to highlight is that these can look quite different between different parts of the US. So here's what it looks like for the Central East Atlantic. And what you see here is that whereas there's a more flat part of the curve in the Southern Plain, in the Central East Atlantic, that part of the curve is steeper. So again, this is something that the model is able to do. Between different regions, we get very different shapes of these curves. But even within the same region, particularly if we look at this one, there are also some subtle differences between the curves. The lower valley of Texas stays flatter for a bit longer and then starts to decline more sharply relative to some of the other regions that we see here. So again, these nuances in the relationships between temperature and mortality and the interplay of that with climate division is something that we're able to tease out with this model. Okay, but now to the punchline, the scenario-based projection. So what we're looking at here is RCP 8.5 versus RCP 4.5. And we're essentially looking at the ratio of mortality rates. Okay, so you might recall that in the equation that I showed earlier, we had the log mortality. And if we were to take the difference of those two functions, all of the other random effects due to climate division and age and the year, all of those things cancel out. And what we're left with is the difference of the two functions for the different temperatures. So if we take that difference and then take the exponential of that difference, we get what we see here, which is a ratio. So numbers greater than 1, so the lighter colors in this plot indicate that mortality will be worse. The colors that are darker indicate that there will actually be mortality improvement. And this, what you see here, is the map for January. And most of these values that you see here, although some of them are a little bit lighter, indicating that mortality gets worse, most of what you're seeing here, particularly around the south, around the coastal regions, the more heavily populated parts of the US, most of these are below 1, meaning that in January, in the more severe climate scenario, there'll actually be a small reduction in mortality. This is the same plot extrapolated out further in time. So now we're talking about between 2060 and 2090. And again, there's some quite dark blue areas here. These indicate up to a 4% improvement in the winter for mortality. So the main takeaway message here, and there are many caveats to this message, which I'll discuss later, but the main takeaway message here is that in January, there will be lower mortality rates for most of the US, and in particular the more densely populated parts of the US, under a more severe climate change scenario. Okay. Now, this is not, I'm not advocating for more carbon emissions by saying this, because we also have to look at the story in summer. And when we do that, this is the earlier part of this century, so between 2035 and 2065. The difference between an average year across that range of years. What we're looking at is the ratio of RCP 8.5 versus RCP 4.5. And now what we see is that some regions in the US, particularly the South, and by South I mean South in the sense of the historical sense of that word in the United States, but also just all along the bottom, parts of southern Texas, parts of Arizona and New Mexico. These are lighter in color, and these are going to experience a deterioration in mortality rates, a worsening of mortality rates in the summer. There are some parts here that are darker in blue, although these are very sparsely populated states. And again, we're talking about very slightly below 1 here. So I would say that these improvements are not statistically significant. So that is in 2035 to 2065. If we look at the same thing between 2060 and 2090, we see a lot more yellow everywhere, including in the Pacific Northwest, which is an interesting one. So the Pacific Northwest may be more vulnerable under the RCP 8.5 scenario to having more deaths in the summer. And again, across the south of Arizona and New Mexico, south of Texas, and these southern states on the East Coast, we see a worsening of mortality rates during the summer. Okay, so just to wrap up the main messages of those visualizations, if there is more severe climate change, if there's a more severe emission scenario, that would be associated with milder winters on average, and that is associated with low mortality rates. And insofar as that's going to happen, the improvement will be more pronounced in coastal regions. On the other hand, climate change will see warmer summers on average, and that's associated with higher mortality rates. And that deterioration in mortality will be more severe in the south, as well as the Pacific Northwest. What are these changes? Well, in January, we're looking at changes on the order of 5% over the period 2060 to 2090. In July, we're looking at an improvement, a 3% increase, I should say here. It's higher mortality, so it's not actually an improvement. A 3% increase in July in the period 2060 to 2090. So those are the orders of magnitude that we're talking about. But of course, it's nice to look at the overall picture. but there are some interesting narratives when we drill down and we look at specific examples. So the first one we're going to look at here is just for 3 climate divisions in one of the regions that we looked at earlier. And in particular, what we're looking at here is the very southern parts of Texas. So the orange and the red lines are 2 of the most southern climate divisions in Texas. And then we're also looking at central Oklahoma, which is not quite as far south, but somewhat nearby, just for reference. And what we see here, so just to be clear what I'm talking about, we're talking about these 2 regions right at the bottom, as well as a region in the middle of Oklahoma. And what we can see here, this is RCP 8.5 versus RCP 4.5 in the earlier part of the century. So we see here in July and August, and to some extent even in June, the mortality rates are higher. And this is happening in those southern parts of Texas because these are very hot regions, and these hot regions will get even hotter. On the other hand, the sort of estimates for central Oklahoma are a little bit flatter, slightly below 1. With milder winters, there'll be a slight reduction in mortality, and the summers in central Oklahoma just don't get hot enough to be associated with that increase in mortality under the RCP 8.5 scenario. If we go further into the century, this gets even more pronounced, okay, because the hot regions get even hotter and the heat waves become even more severe. So again, in Lower Valley, Texas and Southern Texas, we're seeing up to a 2% increase in mortality rates in July and in August. In June, it's also quite high, even to some extent in September. So in these regions that are very hot, this is not a big surprise, but in the regions that are very hot, these are going to be susceptible to more deaths in the summer under a climate scenario, under a higher emissions climate scenario. But if the example were that simple, it would be, it would be interesting, but perhaps not so surprising. Of course, if it gets hotter, then the hotter regions are more susceptible. But what I want to, the second example I want to look at, which is from a different part of the country, and what I want to tease out here, the 2 ones that are of particular interest are going to be southern West Virginia and the southwest plateau of Pennsylvania. So if I just go back to our maps, sorry, just to go back a bit. If I just go back to the map, we're talking about this little corner of Pennsylvania, which is quite close to the state of West Virginia. We're looking at one of the climate regions in West Virginia. And then just for reference, we're looking at Connecticut, which is up on the coast here. So if we just go back to those results, this is the early part of the century, and here everything remains quite flat. But if we now go into the latter part of the century, so from 2060 to 2090, we do see that southern West Virginia is going to have a higher increase in mortality rates under the RCP 8.5 scenario than southwest plateau Pennsylvania. And unlike the previous example, this cannot be purely attributed to the fact that southern West Virginia is hotter than southwest plateau Pennsylvania. In fact, under all climate scenarios, these 2 climate divisions, southern West Virginia and southwest plateau Pennsylvania, have quite similar temperatures. So what this tells us is that southern West Virginia is somewhat more susceptible in the summer to hotter summers. And even though those summers are as hot as the neighboring region of Pennsylvania, the effect on mortality rates is going to be higher in southern West Virginia. I'm just zooming in here. This is the same plot, but just zooming in a little bit, just to make that clearer. So again, the red line and the orange line correspond to 2 climate divisions that actually have similar projected temperatures. It's just that the resilience of southwest Virginia, the orange line, is a little bit worse than it is in southwest plateau Pennsylvania. Now, we can conjecture at possible reasons for that. So again, West Virginia is a state with a fairly high degree of disadvantage economically, and therefore our conjecture is that the socioeconomic status of different regions may have an effect on their ability to withstand the effects of climate change on mortality. So again, the predominant effect, if we had to look at the whole United States, the predominant effect is that, in summer, warmer regions are going to have higher increases in the mortality rate. However, it's not quite as simple as that. There are regions which have similar projected temperatures in July, and we looked at two of them just now, but these will have different projected changes in mortality between the two emission scenarios. And again, it's our conjecture that the socioeconomic status of these states is having an effect on their resilience to climate change. Okay. And the very last thing I'll say, because what we looked at, every result that we looked at just now was looking at an average year under the different emission scenarios. But that's not the only part of the story. For example, here what we're saying, and this is maybe exaggerating the effects a little bit, but here we're saying, what if we were to have a bad year under the RCP 8.5 scenario, but a good year under the RCP 4.5 scenario? And this is what it would look like in the early part of the century. This is what it would look like in the latter part of the century. And again, these are especially in those regions along the south. These are these results are in July. And here we're seeing higher levels of higher increases in the mortality rate between the two scenarios. We're looking at 5% more under the RCP 8.5 scenario, compared to 3% when we looked at average year versus average year. So this is just to indicate that there are different kinds of projections that you can feed through this model and get slightly different results, or in some cases quite different results. But before wrapping up, I do just want to highlight some of the limitations of the study. So not all of the interactions can be modeled. So the main emphasis of today's talk was those interactions between the climate division and the temperature effects. And you could argue that there should be an age temperature interaction, and we don't have that in the model here. Now, there's nothing stopping us from including that in the model. However, just keep in mind that the more of these interaction effects you include, the more parameterized the model becomes, and there's more noise in the estimation. So there are trade-offs just in terms of the model building. But if the focus of your interest was how age and temperature interact, then rather than perhaps having the interaction between climate division and temperature, you would have it between age and temperature. At the moment, the way the results were presented today, we just projected climate averages. So we looked at averages over the period 2035 to 2065 and also 2060 to 2090, and we fed those into the model. What you could also do, although obtaining this data is a little bit difficult, but if you had a detailed climate simulation, you could, in principle, also feed that into the model, and that would give a richer understanding of the effect of extremes. By showing you these results that use climate averages, we lose a bit of the story of extremes. Finally, and I think it's important to say this because, again, in the results, we did see modest increases in mortality rates in summer, and in fact, reductions in mortality rates in winter. And I would just emphasize that we're taking quite a narrow focus here. We're only looking at the effects of climate change on mortality. And of course, climate change will affect a lot of other things, which are important to insurance companies, but also important to society. So, this part of the story doesn't look at what's going to happen with forest fires. It doesn't look at what's going to happen with rising sea levels. And it's important to emphasize that these issues are also very important. So we don't want to downplay the seriousness of climate change by having too narrow a focus on mortality rates. And the final thing, and it's in a similar vein, the model cannot account for these large structural breaks that might arise due to climate change. There may be disruption to food supplies. There may be the emergence of new climate-related diseases. That's not the kind of things that we've been able to look at with this modeling exercise. So essentially what this modeling exercise does is simply take two different temperature scenarios under two different emissions projections, and gives you an understanding of the impact that will have on mortality, assuming we do nothing else, assuming that populations don't move around, assuming that sea levels don't rise in a way that there's climate refugees, assuming that other mitigation effects are not put into place. Okay, so it's important to highlight those limitations of the study. I'm a champion for statistics, but statistics can't answer those sorts of questions. So with that, I think we can wrap it up. I might just stop sharing the slides and open it up for Q&A.
Yes, thank you so much to you both, because it's a very interesting and insightful presentation, and I think it's just strengthened the first result you were presenting. Maybe I have just a first remark which has been made by Colin, and maybe you want to add something. There is a comment from Hanley, which just underlined the fact that awareness may change behaviors. Economists are taking a lot of time looking at change in behaviors, and therefore prevention may, of course, limit the consequences on heat waves, on mortality. Therefore, it could, of course, change the shape of what you were presenting, especially by erasing maybe the worst consequences, making therefore climate change very beneficial in terms of mortality. Sorry for the presentation, which is a little aggressive in my wording, is just in order to underline the consequence. But maybe you would like to add something, Annie or Anastasios Panagiotelis, please.
Yeah, if I can elaborate on Colin's comment, like it is true that the sort of effects of education are not something that can be easily incorporated into a model, and they cannot be easily incorporated into a projection that you're making of what might happen in 50 to almost 100 years. So I would say that the purpose of an exercise like this, though, might be to indicate where it's best to focus those efforts of education. I mean, it's nice if we can educate everyone, but there's a budget involved in that. So if we can identify the regions, and we've done that with some of the regions, where the effects may be more pronounced, and obviously that's in hotter regions, but also in some of these regions that are more socioeconomically disadvantaged, that provides policymakers with a roadmap of where to best focus mitigation efforts and education efforts. So I would just add that remark to the very valuable comment that Colin made.
Please, are there some questions? We have this exceptional opportunity to raise questions and to look at the opportunities and limitation of such studies. Do you have some questions, some further questions? I don't see at this point in time questions. I have probably one. In the past, many economic studies, especially that have been provided for the National Bureau of Economic Research, have insisted on the fact that it's not so much the temperature level that is important than the volatility, that is how you may jump from, let us say, probably not a very good example, from 10 to 30 in very few days or very few hours. But there is one point concerning climate change, is that most of the experts are also...
I need to see why my card is getting blocked on online transactions. Can you connect me to an agent?
Sorry? Maybe it's just an exceptional remark. No, and therefore, because climate change is linked by many experts to more, not only to higher means, but also higher volatility, may this point be included in such studies, or what is your opinion on that aspect of the risk?
Thanks a lot, Philip. Yeah, that's actually a very good point because at the beginning of the presentation when I explained the relationship between temperature and mortality, it is like a more complicated complex relationship rather than just saying, like high temperature, extreme high temperature cause excess deaths and extreme cold temperature create excess deaths. So volatility in temperatures is definitely something that is researched in the literature, and they found some link between high volatility in temperature and an increased level of health risk. So this is already something like you're absolutely right about this point. It's already recognized. On the other hand, the reason why we currently not including such variable in the framework is partly because of the data limitation. When we have mortality data, it's collected at a monthly level, and obviously with temperature data, you have much higher frequency, but we do need to match these two data sets to construct this modeling framework. And we currently having maximum and minimum temperature for these different regions. And I also want to highlight the fact that when people were talking about the average temperature, from a statistical perspective, you may think daily maximum, daily average temperature is, like aggregating the temperature over 24 hours and then take the simple average. That's mostly not the case. And what I heard from people from environmental research is they would simply look at the maximum and the minimum and then take an average. So a lot of the times this short-term volatility is actually lost. And the reason is with this temperature or this weather stations, you actually don't have the data for every hour. Like for certain regions, they may have people manually collecting the data. So data limitation is a big issue. But at the same time, I do think looking at the distribution of the temperature, not only like maximum and minimum, is definitely going to have a more complete picture. And that's something we may consider experimenting within a smaller region where we may be able to find more higher quality data on a higher frequency. And but for a study that concerned the entire contiguous US, it would be challenging to have the sufficient data set to conduct such research. And Tas, do you want to add something?
I do actually. So I would just add that it's actually an excellent question, Philippe, and it opens up a bit of a Pandora's box because the point you make about volatility is not as simple as saying more volatility is bad for mortality, because there is also, it depends on the scale, the time scale at which you're talking about this volatility. Over the course of a year, if it's a very, very hot summer and a very, very cold winter, that is the worst possible scenario for mortality over the course of a year. But if we're talking over a shorter time frame, if we're talking over a week, and if it happens conditional on it being a very hot or a very cold week, volatility is your friend, right? If in the sense that, like I said earlier, if it's a very hot day, but it becomes cooler at night, that is actually less severe because you get some respite from the heat. And we can say similar things in the winter. So at that resolution, at that finer time scale, it's actually the case that you want more volatility in a way. So there's a lot of nuance to your question. Now, when it comes to modeling, we also encounter the kind of data limitations that Han was talking about, because we have to match the resolution of the time resolution that we look at. Do we look at monthly data? Do we look at yearly data? Do we look at daily data? That has to be able to be matched to mortality data, and mortality data is not available daily. And if you look at mortality data yearly, then you lose that seasonal fluctuation completely. So by going monthly, we feel like we kind of found the right compromise. But at that scale, it's difficult to say whether volatility is your friend or your enemy. So it's definitely a very good question, and one that does open up a lot of other questions, unfortunately.
Thank you very much, and you just underlined that the question is much more complex than I thought. As always, one word, volatility, is covering many dimensions of the trust, and therefore we can end up with very different conclusions. But what I infer from what you have been saying is that main drawback in terms of availability of data is on the side of mortality, because for such a country where we have a good database with the CDS, for example, etc., that is the US, we are not able to go beyond monthly mortality data, which is of course a lot, but which is probably not totally sufficient in order to appreciate how much shorter term volatility would end up. But having in mind your remark, Anastasios, that if we look at very, very short term volatility, then it's less an enemy than a friend of survival. Okay, maybe are there other question, or maybe you want Hanli and Anastasios Panagiotelis to add something to this first remark on this point? Otherwise, I look if there are questions. Please, I will just suggest to benefit and profit of the availability of our friends to your question. It's an extraordinary opportunity to ask question.
So the other thing I would
yes,
just remind all
please,
participants that they should feel free. They may not have questions right now, but if questions arise later on, I want to make sure that you all feel free to contact us via email, and we can always answer questions that way if they come up later.
Yes. I insist on that point. Firstly, if you need the address, we can share the address with you. You will in any case find the address in the report, therefore, which are on the website of the foundation. And in any case, if you want something, just send us a mail. May I have just another question? Maybe the question you said, of course, the interaction between age and temperature has not been exactly searched for. Is it therefore that your results are perfectly available as such, as long as I assume that the structure per age of the population is not dramatically changing? Or is it a wrong conclusion from the limitation you were describing?
So I would say we do control for age, but we control for age as a fixed effect, as a random effect for each age group. So obviously mortality rates are higher for older age groups and lower for younger age groups. There is also some interaction with the year and age, but what we're not looking at in this particular model is an interaction between temperature and age. Now, what that means is in the main results that we showed you, any effects that are due to age are differenced out when we just look at the effect of different temperature scenarios. Because effectively what we're saying, and I think this is an assumption of the model, and maybe one that is problematic, but the assumption of the model is that temperature does not impact age beyond the existing random effect for age. Now, we could adjust the model to look at that, but our emphasis in this study was to look at the interplay between temperature and climate division. In future iterations of the model, we may look at that. The only problem becomes all of these things potentially interact with one another. And the more of these two-way and three-way effects that you include in the model, not only does the interpretation become more difficult, but the estimation becomes more difficult. So there is a trade-off there. But of course, if the main emphasis of what we wanted to talk about today was the interplay between age and temperature, which I do believe is there, then we would have estimated a different model.
Is it therefore that with aging, I should just take your result with a certain dose of caution or not? Because it's probably our main question and main challenge, which is aging, and therefore we have to consider if it is changing or not your result marginally. Then there is nothing to add or more profoundly.
So again, all of our results are shown as a difference between two different emission scenarios. Now, so any changes that happen in aging are assumed to be fixed across those two different scenarios. So it's not that there may be changes in the in the composition of the age groups, but we assume, but because we difference between two different climate scenarios, as long as those ages don't interact with the climate scenarios, right? Then they can be different.
It's clear.
Yeah,
it's clear. Yeah. It's very clear. Yeah. Therefore, you have implicitly been taking into account that the fact that there is some aging, especially in some areas in the US, which are more populated with older people, but if there is any interaction between temperature and age, then of course, if for example, higher temperature are favorable for becoming older and surviving longer, etc., this is not taken into account in your rate.
Not. Yeah.
No.
Correct.
It's clear.
Yeah, and I think I would also like to add, to emphasize again, based on in the current modeling framework, we only consider older age groups from 55 onwards. So we have a few different age groups, but we're not really considering people younger than 55, for example. So because this is based on existing literature on how extreme temperatures affect mortality, and the younger age groups, you can see the impact is really minimal. It's really kind of not there. So therefore, we restrict ourselves to only look at older age groups.
Yes, of course. Please, I am just looking. Do you have more questions? I look at who may be rising. Raise your hand. I just look. Saying, do you see someone raising the hand? You don't see it? Maybe, perhaps, therefore, if there are no further questions, a last question, which is a kind of concluding question, which is, what are the perspectives you see for your study? How would you, in the future, enlarge, develop, of course, taking into account other countries, taking into account other dimensions? I just let you, what would you suggest, and what will you be prepared to investigate on your side?
I'll let you go first, Han.
Okay, cool. Yeah, so I actually do have ongoing projects, current projects, investigating the same topic on climate or temperature related mortality. So one of the direction we're going is actually touched Philip's comments earlier, which is about the variability in temperature. We're not directly looking at the variability, but we're looking at the lagged impact of temperature, which is if you have temperature at a higher a frequency. I mean, obviously the modeling framework is different. If you look at the temperature on on a daily basis, but having mortality on a weekly basis, you can incorporate the temperature information over the last 21 days, and then look at what's the aggregate, what's the total impact on mortality for temperature over the last 21 days. So that's one of the ongoing project I'm doing, assessing the lagged impact of temperature on mortality. The other project that actually Tas and we discuss about doing is to create a temperature index that is particularly designed to measure the level of mortality risk result from temperature. So again, that kind of touch on Philip's comment earlier, is about the distribution, what type of distribution of temperature over time that has the most adverse impact on mortality. So this is another project we have in mind, because we acknowledge the complex relationship between temperature and mortality, and we just want to go one step further in looking at maybe it's like a consecutive hot days, like which will be a heat wave that's impacting mortality, or maybe like a consecutive number of cold days, or maybe like, you have a fluctuation, you have volatility in temperature within like a short period of time, etc. We're trying to create a temperature index that particularly for measuring the level of mortality risk resulting from temperature. So these are the two ongoing projects we're doing. And for the first project I was talking about, we're actually using the European data. So fortunately for the European data, we're able to get weekly frequency death data and daily frequency temperature data.
Yeah. So again, just to elaborate on that, currently what the best we can do at the moment is to try and harmonize the frequency at which we observe mortality data, which is typically a low frequency, at best monthly, or in some cases weekly. But then if we think about temperature data, we can measure that at a very high frequency. I mean, I have an app on my phone which tells me the temperature every 5 minutes. So this resembles a problem, and I know, Philippe, you you're an economist, and this is a problem that we face in economics called mixed frequency data. For example, some economic measures are only released quarterly, but stock prices we can have every 5 minutes. So a lot of techniques have been developed to, rather than summarize the high frequency data into low frequency data and harmonize the data, we actually deal with the different frequencies in which the data are measured at as part of our modeling. So there's some very exciting techniques there, and we may be able to bring them into these sorts of problems. So that's where we see this is going.
Yes, I think it's very, very interesting. I think we are just at the end of our webinar. I will, before greeting you, I will just report a remark made by one participant. Thank you for staying up way past midnight to share your results with us. Very much appreciated.
No problem.
Yeah.
And of course, for all the auditors and the audience, I will insist on the fact that you are very late when in Europe we are not so much late. And I would like to thank you very much and to insist on the quality of your work and the very stimulating job you have done and your stimulating conclusion. And we hope to remain in a relation and to continue to follow your work. Thank you so much.
Merci beaucoup.
Merci beaucoup.
Thank you, Philippe. Thank you,
you,
Zing. Thank you,
everyone.
everyone, for your interest in our project.
Thank you.
Goodbye.
Goodbye.
Bye.
Goodbye.